Again, welcome to Mathematical Structure for Computer Science, CS113, also known as Discrete Mathematics. In these lectures, we'll go through Mathematical Induction, which is again Unit 5, Lecture 1. That's Chapter 5, Section 1. So in this section, we're going to talk about mathematical induction, the definition, and also the meaning. Also, we'll look through some of the examples of proof by mathematical induction and also mistaken proofs by mathematical induction. Also, we'll go through the guidelines for proofs by mathematical induction. So first, we start with an example. The example here is cramming an infinite letter. So this is the concept of, again, mathematical induction. So suppose we have an infinity ladder, and we can reach the first rung of the ladder. Again, if we can reach a particular rung of the ladder, then we can reach the next rung. So what we mean here is that if I'm in step 1, I can move to step 2, and I can move to step 3, and we keep going. So here we say from 1, that's from step 1, we can reach the first rung. Then by applying 2, we can reach the second rung. Applying 2 again, we can reach the third rung, and so on. So we can apply 2 any number of times to reach any particular rung, no matter how high up. So we can see the steps 1, 2, 3, all the way. So this is an example that motivates proof by mathematical induction. Here we can prove that if we are in step 1, we can move to step 2. So for example, if we are in step K, if it's step K, then step K plus 1. So that's the principles of mathematical induction. Here we say that the principles of mathematical induction, that is to prove that P at n is true for all positive integers n. We complete these steps. So the basic step, we will show that P at 1 is true. So if P at 1 is true, the inductive step is to show that P at K, if P at K, then P at K plus 1, which means we can move from P at 1 to P at 2. And this will be true for all positive integers, because if P at K and K is 2, then we can go to P at 3, which will be 2 plus 1. If K is 10, it will be 10 plus 1, 11. So we said this condition will be true. P at K, if P at K, then P at K plus 1 is true for all positive integers. Because if we have a negative integer, for example, K is negative 1, then P at K will be negative 1 plus 1 is 0. Now to complete the inductive step, we are assuming that the inductive hypothesis that P at K holds for an arbitrary integer K, which shows that, again, P at K plus 1 must be true, which is if P at K, then P at K plus 1. It's always true for any positive integer. So we have a basic step, P by 1, we can reach rung 1. The inductive step will be assuming the inductive hypothesis that we can reach rung K, then by 2 we can reach K plus 1. So hence we have if P at K, then P at K plus 1 is true for all positive integer K. We can reach every rung on the ladder. Because again, if it's 1, the next will be 2, the next will be 3. So P at K, then P at K plus 1. So if K is 10, then we go to 11. So this will be always true for all, again, positive integers K. So the important points about using mathematical induction. Here we say that the mathematical induction can be expressed as the rule of inference. So example here we say P at 1 conjunction or K. If P at K, then P at K plus 1. So here we say if we are in step 1, then next will be step 2. P at K, then P at K plus 1. This is true for all n at P at n. So if we have P at 1 and all K, P at K, then P at K plus 1, then we have all n at P at n. And here, again, the domain of the set of positive integers. All the values for K should be, again, positive integer. Here in a proof by mathematical induction, we don't assume that P at K is true for all positive integer. We show that if we are assuming that P at K is true, then P at K plus 1 must also be true. So here we are not proving that or assuming that P at K is always true for all positive integer. But we are trying to say that, like cramming the letter from first step, we go to the second step, we go to the third step. So here we are trying to prove that if P at K, then P at K plus 1 must be true. If P at K is true, then P K plus 1 must be true. Now, proofs by mathematical induction, again, do not always start at the integer 1. In such case, the basis step begins at the starting point B, where B is an integer. We will see some examples soon. But the whole concept here is that in mathematical induction, we have two parts, the basis and then the inductive. So we can see example here, basis step, inductive step. Basis step is the lowest unit. So here we start example with P at 1 is true. Then P at 1 plus 1 is true. Here we are assuming K is 1. So always the basis is the beginning. But here we are saying that we don't have to start from 1. We can start anywhere. It can be 10, 20, but that is beginning. So that's what we are saying here, that in a proof by mathematical induction, we don't assume that P at K is true for all positive integer. We show that if we are assuming that P at K is true, then P at K plus 1 must also be true. And the proofs by mathematical induction do not always start at the integer 1. In such case, the basis step begins at the starting point B, where B is an integer, can be any value. So the validity of mathematical induction, here we say mathematical induction is valid because of the well-ordering property. We states that every non-empty subset of the set of positive integer has at least element. Again, we state that every non-empty subset of the set of positive integer has at least one element because it's non-empty. So suppose that P at 1 holds that P at K, then P at K plus 1 is true for all positive integer K. Now we can assume there is at least one positive integer n for which P at n is false. So if that is the case, then the set S of the positive integer for which P at n is false is non-empty. It's non-empty. Also, by the well-ordering property, S has at least element. Let's say it's M. So we know that M cannot be 1 since P at 1 holds. And since M is positive and greater than 1, then M minus 1 must be a positive integer also. And since M minus 1 is less than M, we will say that it is not in X. So P at M minus 1 must be true. And also, since the conditional P at K, then P at K plus 1 for every positive integer K holds, we can also say that P at M must also be true. This will contradict P at M be false. So we know P at N must be true for every positive integer. So we have an example here. This is a dominus. So if we have a domino, let's say 100 dominoes, we start from 1 to 100. We can see that if they are arranged in vertical order, if we pull or we push 1 and it fall on 2, again 2 will fall down, then 3, then 4, all the way to the end. So this is like repetition of the same step. So here we say consider an infinity sequence of dominoes. We label the dominoes as 1, 2, 3, etc., where each domino is standing. Now let P at N be the proposition that the nth domino is knocked down. So now we know that the first domino is knocked down, that is P at 1 is true. We also know that if whenever the kth domino is knocked down, it knocks over K plus 1 domino. So this will be P at K. If P at K, then P at K plus 1 is true for all the positive integers. Because if 1 falls, it will knock 2, 2 will knock 3, and we keep going. Hence, all dominoes are knocked over. So P at N is true for all positive integer N. Now let's prove a summation formula by mathematical induction. Here they say we should show that the sum from 1 to N is equal to N, then N plus 1 over 2. Now let's see the basis. The basis will be P at N, P at 1. So if P at 1 is true, we plug in P at N, N is 1. So we plug in 1, 1 plus 1 over 2. And that also gives us 1. So which means it's true. P at 1 is true since 1 plus 1 over 2 is 1, also is true. This is my lowest step, which is 1. Then that's the basis step. Now for the inductive step, we were assuming that true for P at K. So we still get I from 1 to H. Sorry, from 1 to K, we are using K, P at K. From 1 to K, it will be K, then K plus 1 over 2. So under this assumption, we can say we start from 1 plus 2 plus 3 all the way to K, then K plus 1, etc. So to find the summation, we can say K multiplied by K plus 1 all over 2 plus K plus 1. Now we'll bring 2 here for K plus 1 so that we divide everything by 2 instead of only dividing K squared plus 1 and K by 2. So we have 2 here, then we divide everything by 2. Then we can solve the parentheses. We have K plus 1, K plus 1. So we factorize by grouping. So we get K plus 2 times K plus 1 all over 2. Now we also have conjecture and proof correct a formula for the sum of the first and positive odd integer. Then prove your conjecture. So yes, conjecturing and proving correct a summation formula. So if I have 1 equal to 1 and 1 plus 3 is 4 and 1 plus 3 again is 5. 1 plus 3 plus 5 is 9. 1 plus 3 plus 5 plus 7 is 16. 16, 1 plus 3 plus 5 plus 7 plus 25. And we keep going. Here, we can conjecture that the sum of the first n position odd integer is n squared. So we get 1 plus 3 plus 5 all the way to 2n minus 1 plus 2n plus 1, all equal to n squared. So we can prove that the conjecture is proved correct with mathematical induction. Here we say the basic step will be p at 1 is true since 1 square equal to 1. Then the inductive step will be p at k is k plus 1 for every positive integer k. And also we're assuming the inductive hypothesis holds, and then show that p at k plus 1 holds as well. So we also have the inductive hypothesis. Here we have 1 plus 3 plus 5 plus 2k minus 1, all equal to k squared. So here we are assuming p at k is followed at 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1 equal to 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1. So by solving this, we get k squared plus 2k plus 1, which will give me k squared plus 2k plus 1. And when I factorize it, I'll get k plus 1 all squared. We also can prove inequalities. So for example, here they say we should use mathematical induction to prove that n is less than 2 to the power n. So here we are going to test some values for n and see. So solution, we say let p at n be the proposition that n is less than 2 to the power n. So the basic step will be p at 1. So if p at 1, we can see that we have 1 less than 2 to the power 1, which is 2, so it's true. Then the inductive step will be assuming p at k holds that k is less than 2 to the power k for an arbitrary positive integer k. Here, not all the positive integer k. So here we show that p at k plus 1 will hold, since by the inductive hypothesis k is less than 2 to the power k, it follows that k plus 1 less than 2k plus 1 is less than or equal to 2k plus 2k, which will be 2 times 2 to the power k, which will give me 2 to the power k plus 1. So we know the base is 2, so k plus 1 will give me 2k plus 2 and then 1. So yeah, at the end we will see that the solution will be 1 less than or equal to 2 to the power k plus 2k, which will give me 2 times 2 to the power k equal to 2k plus 1. So here we can say that n is less than 2 to the power n will holds for all positive integer, just by looking at the steps here. So another example, we should use the mathematical induction to prove that 2 to the power n is less than n factorial. So first thing we will do, let p at n be the proposition that 2 to the power n is less than n factorial. So the basic step here, we say for all n greater than or equal to 4. So we are not going to start from 1, 2, or 3. They say equal or greater than 4. So we test our condition from 4. So we can see that we say that assuming p at k holds, then 2 to the power k is less than k for an arbitrary integer k is greater than or equal to 4. Now to show that p at k plus 1 holds, we will get 2 to the power k plus 1 equal to 2 times 2 to the power k, which will give me 2 times k factorial by inductive hypothesis. And that will give me k plus 1, k factorial, and k plus 1 factorial. Therefore, 2 to the power n is less than n factorial will hold for every integer n is greater than or equal to 4. If n is less than 4, then it will not hold. 2n to the power less than n will not always be true. Also, proving divisibility result. Again, division or divisibility result. Here we are assuming we are going to use mathematical induction to prove that n cubed minus n is divisible by 3 for every positive integer n. So the solution will be p at n can be a proposition that n cubed minus n is divisible by 3. So the basis is that p at 1 is true since 1 to the power 3 minus 1 is 0, which is divisible by 3. But in the inductive step, we are assuming p at k holds, that is, k cubed minus k is divisible by 3 for an arbitrarily positive integer k. Now to show that p at k plus 1 follows, here we get k plus 1 cubed minus k plus 1, and by opening the parenthesis here, k plus 1 all cubed is the same as k cubed plus 3k squared plus 3k plus 1. Then minus the k plus 1. We combine the two terms and we factorize. So we get k cubed minus k plus 3k squared plus k. So by inductive hypothesis, the first term k cubed minus k, we can say is divisible by 3. And the second term is divisible by 3 since it is an integer multiplied by 3. So by part 1 of theorem 1 in section 4.1, we can say k plus 1 cubed minus k plus 1, both is divisible by 3. Therefore, n cubed minus n is also divisible for every integer positive integer n. So this is the number of subset of a finite set. For example, here they say we should use mathematical induction to show that, again, the goal of mathematical induction is to prove a theory is true. Always proving that a fact is true. So we are using mathematical induction to show that if S is a finite set with n elements, where n is non-negative integer, then S has 2 to the power n subset. So the solution is that let P at n be the proposition that a set with n elements may have or has 2 to the power n subset. So the basis step will be n p at 0 is true because empty set has only itself. So 2 to the power 0 is 1. Inductive step, here we are going to assume that p at k is true for an arbitrarily non-negative integer k. Now the next step is an incorrect proof by mathematical induction. So we use the example to explain this section. Here we have p at n is the statement that every set of n lies in the plane, no two of which are para, and also you have to meet in a common point. So here we say the basic step then should be the statement p at 2 is true because any two lines in the plane that are not para meet in a common point. Then so that will be our basic step. We say n should be greater than or equal to 2. So we start from p at 2. It's true because any two lines in the plane that are not para will meet in a common point. Now in inductive step, we say the inductive hypothesis is the statement that p at k is true for the positive integer k greater than or equal to 2. That is, every set of k lies in the plane. So no two of which are para meet in a common point. Because if they are para, there's no way they will meet. They will be para throughout. Also, we must show that if P at K holds, then P at K plus 1 will also hold. So we say if P at K is true, then P at K plus 1 also is true. In inductive hypothesis, we say every set of K lines in a plane where K is greater than or equal to 2. Also, no two of which are para. So they meet in a common point. Here we should consider a set of K plus 1 distinct lines in a plane. No two para, but by the inductive hypothesis, the first K of these lines must meet in a common point, P1. By the inductive hypothesis also, the last K of this line must meet in a common point again, if they are not in para. Now, if P1 and P2 are different points, now all lines containing both of them must be the same line because 2 points determine a line. This contradicts the assumption that the lines are distinct. Hence, P1 equal to P2 lies on all K plus 1 distinct lines. And therefore, P at K plus 1 will hold. Also, assuming that K is greater than or equal to 2, the distinct line meet in a common point, then every K plus 1 lines meet in a common point too. And here there must be an error in this proof since conclusion is absurd. But where is the error? So our answer is, if P at K, then P at K plus 1 holds, only hold for K greater than or equal to 3. It is not the case that P at 2 implies P at 3. And also the first two lines must meet in a common point, P1. And also the second two must meet in a common point, P2. And they do not have to be the same point, since again, only the second line is common to both sets of lines. So this is the general guidelines for mathematical induction proof. We have 8. First, they say we should always express the statement that is to be proved in the form of, for all n greater than or equal to b, P at n for a fixed integer P. So now for all n greater than or equal to P, P at n for a fixed integer B. Also, we should write out the worst basic step. Then show that P at B is true, taking care that the correct value of B is used. This also completes the first part of the proof. Next, we need to write out the worst inductive step. Then state and clearly identify the inductive hypothesis in the form, assuming that P at K is true for n arbitrary fixed integer, K greater than or equal to B. We also need to state the needs to be proved under the assumption that the inductive hypothesis also is true. That is, we need to write that P at K plus 1 says. Now, prove that P at K plus 1, making use the assumption P at K. So if it's P at K, then P at K plus 1, both are true. And here they say we should be sure that our proof is valid for all integer K with K greater than or equal to B, which will take care that the proof works for small values of K, including K equal to B. Then we should also clearly identify the conclusion of the inductive step, such as by saying this completes the inductive step. After the basis step and the inductive step, we need to state the conclusion, namely that by mathematical induction, P at n is true for all integers n with n greater than or equal to b. So again, this will be our conclusion for chapter 5 or the unit 5, section 1 of the course. We're starting with the mathematical induction. In these lectures, we learn the definition of mathematical induction and why do we use it. Especially in computer science, it's very common, even with recursion, also recursive function. Now with mathematical induction, the function we always have two parts, the basis part and the inductive part also. The basis tells us the minimum beginning of the variable. So we can say P at 1, the next will be P at 2, 3, etc. So again, wish everybody the best and hope to see you in the next lectures, which will be the continuation of mathematical induction, unit 5, section 2. Thank you and have a good one.